Okay, so we're doing best fit curves. So we did linear regression that was fitting a straight line. Sometimes the data is best fit using a polynomial. So let's look at a polynomial of order m. Okay, polynomial of order m, like the one shown here, has m plus 1 constants, c0, c1, c2, so on to cm. Like before, we formulate an optimization or a minimization problem. We want to minimize E. So what we do is we use calculus to write m equations for the m constants. Sorry, m plus 1 equations for m plus 1 constants. So for E to have a minimum, the derivative of E with respect to the constants C0, C1, all the way to M should equal to 0. Okay, so the error term here is basically the difference between the data point yi and the prediction which we get from f of x, so f of xi. And this is just 1 point. Xi is just 1 point. So we need to take the sum over all the m points. So you take the sum, you take the square when you put I equals 1, take the sum of squares, do it for 2, do it for 3, add it all up, and then you get the error. So now when you do dE dC, that is the first derivative, we have 2 summation I equals 1 through n, because there are n data points. C0 plus C1 xi plus so on till Cm xim. Okay, so that's just the derivative of this whole expression. You'll get the 2 coming out, and then we need to take the derivative of the term of essentially df with respect to C0, or rather the whole thing with respect to C0, but yi is just a constant. So the derivative of that will just be C0. Right? This is just the chain rule. Sorry, derivative of C0 with respect to C0 is what we'll get, will be basically be 1. So that's all. Okay, my bad. There's a minus C0, so it'll be minus 1, not plus 1. So this equals 0. Then I do dE dC1. So again, when I do that, it'll be 2 summation I equals 1 through n yi minus C0 plus C1 xi plus so on till Cm xim. And then I need to take the derivative of this whole thing, essentially df xi with respect to dc1. But when you take the derivative, you'll see that everything except for the term which has c1 x1 will be non-zero. So the derivative of negative c1 x1 with respect to c1 is negative xi. So that will pop off here. And you can see that there's a pattern emerging. So the next one, we can just write it quite easily. It's going to be 1 through n yi minus c0 plus c1 xi plus so on cm xim. Then there will be a derivative of the term which is here with respect to c2. So that would be and of course there's a negative, so negative xi square. Yeah, so we keep doing this till we reach dE dCm equals to summation from 1 to n yi minus c0 plus c1 xi plus so on cm xim minus xi That's the last term will show up here. Okay, so we have, by taking the derivative with respect to C0, C1, C2, so on till Cm, we have generated m plus 1 equations, and note that there are m plus 1 unknowns, okay, or constants. So these are C0, C1, so on till Cm. Okay, so what we can do in this case is we can nicely pluck out C0, C1, C2, because you notice that C0, C1 are all constants. So we can actually write a matrix from all these equations. The matrix would look something like this. In summation xi square, so on till summation xim. And then the same thing would be transposed. So summation xi square, summation xi cube, so on, the summation xi m plus 1, summation xi square, summation xi cube, summation xi 4, all the way till summation xi m plus 2. Eventually, we'll get xim, xim plus 1, xi m plus 2, xi m plus m, so it'll be 2m. Okay, then we've done this because we want to isolate the C's. So C0, C1, C2, all the way Cm equals what comes here is summation yi, summation xi yi, summation xi square yi, and so on till summation xim yi. Okay, so just to make it look better, so what we have here is m rows. You can count here, sorry, m plus 1 rows, and then m plus 1 columns, m plus 1 constants, m plus 1 on unknowns, well, knowns on the right side. So this can be written as an equation of this form: a c equals b. So if you want to solve for c, it's going to be a inverse b, where this c is c0, c1, c2, cm. Okay, now you could solve for C using some of the methods we've talked about before: Gauss-Jordan, Gauss-Seidel, Jacobi, and so on. Or you could just use a / in octave. Okay, with this, let's try to apply this and solve a problem. Okay, I did some work this time and I just put this down. This is basically some XY data, and the question is obtain a third order polynomial fit to the data shown on the right. Okay, so we are after this polynomial. That's what we want to fit. That's the data. And as I said, why polynomial? It turns out that, and I'll not do this now in the class, but last time when I had data and I asked linear fit, I actually plotted the data, just this data, and looked at the trend and seen if linear regression was appropriate. You would need to do a similar thing, take the data, plot the data, and look if a non-linear function is appropriate. In this case, a third order polynomial is appropriate, so that's why we'll use the third order polynomial. Okay, so this is basically an exercise in computation. We want to write the equation as AC equals B, where A would be n summation xi summation xi square summation xi cube. Okay, I just took the formula from the previous section, and then that's the one which we just derived, and then put m equals 3, and this is what I get. That's the first column. Then we have summation xi square summation xi cube summation xi raised to 4 summation xi square cube 4 5 summation xi cube xi raised to 4 5 6 Okay, that's A. And then B is summation yi summation xi yi xi square yi. Okay, so to find all these things, what you will have to do is these are essentially your x1, x2, x3, so on till 3, 4, 5, 6, 11 maybe. Yeah, x11, right? So for example, to find summation, but n is 11, you could put 11 here. This is 11. There are n 11 terms. To get summation xi, you will take this, just add it up. Right? So when you do summation xi, you'll do x1 plus x2 plus so on till x11. Just add all this thing up. You'll see that it is actually symmetric, should come out to be 0. Then to find summation xi square, you will take x1 square plus x2 square plus so on, x11 square. That comes out to be 17.6, and so on, right? So it's just a exercise in computation here. The easier way to do this is probably Excel, or if you like MATLAB too. Octave will also do it. What I would do is I would set up these tables. If you're using Excel, write a table for xi square, xi cube, x raised to 4, and so on, and then just use the Excel function to add. Or if you like code, then it's also not very hard to write a code which will just essentially take the squares of them and then sum it up. So you need to do this for that. You need to do this for xi. So you need to do then summation yi, which will be y1 plus y2 plus so on till y11. Turns out that is equal to 24.4093. And then you can do xi yi, which will be x1 y1 x2 y2 plus so on x11 y11 comes out to be 57.11. Anyway, so I'm just writing down a few things so that way you know what's going on and how these computations are done. Okay, this is just one way of doing it. Another way is to actually write columns down and then just use summation. Okay, so once you do this calculation for each of these terms, it's a 4 cross 4 matrix. Luckily, you don't really have to do 16 calculations, right? Because 16 elements. You can see that this and this is the same, right? Then this one and this one's the same. So you only need to compute a few of them. I think you need to go x cube, 4, 5, and 6. That's it. So you need to go up to the power of 6. Okay. Once you have those, let's remove this. So once you compute the ones highlighted in yellow, 1, 2, 3, 4, 5, 6, you basically got the entire matrix. So instead of 16 numbers there, 4 cross 4, you only need to compute 6. Right? Yeah, just 6. It's doable. And then, unfortunately, here you, however, have to calculate all these. Okay, this is not this x square I is not this x square times y. They don't do that mistake. It's basically you need to take element y's and then add it up. So don't make that mistake. So it's going to be those 4 also need to compute it. Anyway, so once you do that computation, you get a matrix which looks like this. 11, 0, 17.6, 0, 0, 17.6, 0, 50.1248, 17.6, 0, 50.1248, 0, 0, 50.1248, 0, 168.0589, C0, C1, C2, C3, and then 24.4093. Okay, so we can solve for C0, C1, C2, C3 by inverting that 4 by 4 cross 4 matrix. You get minus 0.40, so 4279, 1.0453, 1.6544, 0.7724. Yeah, question.
Oh yeah, just a quick question. Earlier you had the matrix A and B at the top,
Mhm.
right? Just a quick question. If you go back up to those, that matrix, my question is, give me 1 second. Are we multiplying? Oh no, it says AC plus B. What's C equal to? Oh, that's a constant, right?
Yeah, the constants C0, C1, C2, and C3. I wrote them down. I think I wrote them down here. This is C. So maybe I'll write it down here. So it'll be very clear.
Thank you.
So this is A, this is C, this is B. And this is C equals A inverse B. Okay, so it's important that you finally write down the equation, it's minus 4279 for constant, then there'll be 1.0453 x plus 1.6544 x square plus 0.7724 x cube. So we have data, we have the equation, which is wrote down. You could take both of them together and just do a plot. I did this offline, and I'm just going to show you what it looks like. Okay, so the blue dots are, it's the original data. Okay, so obviously you want to plot that data before you can go with the judgment call on what's a good way to fit it. So maybe a quadratic would also have done a decent job. I chose a third order polynomial. Clearly, it's not a linear fit, right? You can't draw a straight line, which will explain that trend. So simple is always better. So given a choice, you want to try quadratic first. Then you want to go for third, fourth, fifth order. If you want to figure out after you do quadratic and after you do third order, fourth order, whatever, if you want to make a judgment call, which is a good fit, you could look at the plot and say, okay, I like this one because it explains the data. And of course, go for the simplest one. Another metric you can use is, what are we trying to do here is we're trying to fit the equation such that our fit is based on the fact that we want to reduce the error. There's some metric which gives him the error. So you could use that as a judge. You could use that to judge if the error for a second order fit is obviously going to be larger than the error for a third order fit because you have more flexibility with a third order polynomial. You could use this to make a judgment call whether which fit you like. Sometimes you only get a very little reduction with a third order polynomial than a second order, in which case you might just say simplicity is the best. Let me stick with the second order. Always try to get simple explanations, right? So simple curve is better than a complicated curve. Okay, any questions on this? Okay, so what I've done is for linear regression, if you remember, I wrote code to use there's a function called fmin_unc, unconstrained optimization, to do linear regression. So what I did for the homework is that I told you to do a curve fit for third order polynomial, and I told you to use fmin_unc to check that. I think that's in the homework question. So that way, you could actually take my code and modify the polynomial. It'll work just fine. That's what I think. It'll work for this curve. In fact, you could take the same equation, same code which I gave you, modify that to be a third order polynomial, and it should give you the same answer. It should give you the same answer. If it doesn't give you the same answer, it probably means that it's not converged, fmin_unc, which means you need to tune it. What we have here is actually, I mean, you can't do better than this because this is based on calculus, and the calculus which we have here holds. Now, fmin_unc does some kind of a numerical approximation. It finds gradients and so on. The accuracy of those gradients determine how good your fit is. So if the gradients are inaccurate, then a fit will be inaccurate. So I think that worst case, fmin_unc will do worse than this, but it will never do better than this. Okay.